sum. But it's not just a sum. It's a limit of a sum. What?
Did you say shoot?
No, I don't think I said a bad word. Right? If it was just a sum, I would just write sum. But because it's a limit of a sum, that's a little special. So I'm going to give it a special symbol. I'm going to give it that symbol right there. So when we see that symbol, when you see that symbol in calculus, it's a summation that we're applying a limit to. That's what that represents. So when you get to Cal 3, if you take Cal 3, you see double integrals. It's a double summation. There's two summations. Both of them are having limits applied to them. If you have a triple integral, it's 3. And that's just because of the dimensions that you're working in. Double integrals are usually for 2D, and triples are for 3. But it's beyond what we're talking about now. It's when you see that symbol, you need to be thinking summation and a limits applied to it. Then somehow A and B are important in this formula, right? And it's important in that formula, so we better keep track of them. So why don't we put A down here and B up here? This right here, isn't that just asking you to plug some values into the function? Like we had a number line, here was A, here was B, we had all these rectangles in here, and we were just picking off these right endpoints. All those endpoints were just x values, weren't they? Just some x values. So how do I tell you that what's next is just numbers plugged into a function, right? F of x, that's what it is, right? Evaluate the function at some points. And then this last part, isn't that how wide each of the rectangles were? Right? Pardon? It's, yeah, we know that it's the same, right? To jump from one rectangle to the next. So you can almost look at it as our change in x. Delta x, that's like a physics notation. Delta x is how much our x changes by each time, right? But because we're letting n go to infinity, that delta x goes to 0, doesn't it? It goes and it becomes infinitesimal. And when you let delta x become infinitesimally small, we change the notation to dx. So everything in that formula, I hope now, makes a little more sense. This is saying, hey, add up a bunch of, I almost said it, add up a bunch of crap. I can say crap, that's not vulgar, right? So add up a bunch of crap. What am I adding up? I'm adding up a bunch of widths of rectangles times heights of rectangles, which gives me areas of rectangles. Add them all up, and that's going to give me an area under the curve. And that should be equal to capital F of B minus capital F of A. And that's our big result today. When we see a definite integral, right, that's a definite integral. That's what I told you it would look like. Now we have some geometric idea of where it comes from. When we see that, we use the fundamental theorem of calculus and the evaluation theorem. We need to find the antiderivative. We need to plug in the two endpoints, and we're done. Now, the reason why it's so important for you to understand this formula, that this is really just height, and this is really just width, is because as we advance through this next chapter, we're going to be trying to find some weird stuff. We're going to be trying to find volumes of things that have been wrapped around axes and all this stuff. And it's going to look very complicated. But when you can break it down, like this, like what does each piece represent in the formula, it's a lot easier to approach the problem than to just look like, oh, it's just f of x dx, but I have no idea why it's that. It's just, that's what it is. The fundamental theorem, well, Riemann, see, the great thing about the Riemann sums is that Riemann came along in a time of computers. So he could, what the computer could do quickly is arithmetic. So Riemann could compute areas to any approximation he wanted to. I mean, the computer couldn't go to infinity, but at some point you go far enough and your answer's close enough that you're happy, right? And like I said before, if you look at the big scheme of things, finding antiderivatives of functions is not necessarily easy to do. It's not an easy thing for all functions.
So what are they trying to prove of his theorem that...
That's like me speaking some weird dialect that nobody has ever heard of, like my own dialect, and trying to explain it. No, it's really way out there. Like, I don't even have a full grasp of it. It's not something that you just, oh yeah, that's it. You know, it has to do with complex variables. It's trying to find the zeros of a function. So it's like the x-intercepts of a function, but this function is not defined like a function you would normally think of. It's an infinite sum of functions, but then there are also complex variables, complex numbers, so you're living in a complex plane instead of on a number line. You have to use like extension theorems to just even state the problem. It's very difficult to understand the problem. But one of the results of the Riemann hypothesis is this, and this will blow your mind. What's 1 plus 2 plus 3? 6 plus 4, 10 plus 5, 15 plus, what if I keep doing this forever? Add all the numbers up forever. What's the answer? Infinity? That makes sense to you? Negative 1/12 is what we observe in nature, and it's what physics, a lot of like quantum physics, need that to be true. And a lot of I know that doesn't make any sense to you. I mean, it doesn't make sense to most people, but one of the results of the Riemann hypothesis would prove that that's true. So that's how far out it is. Like it's way out there. All right, I'll give you a nicer problem. If you want a nicer problem that is within, like, it's easier to state, I'll give you a different problem if you want, but not right now. I'll show that to you later. When we get into sequences and series, I'll actually prove to you that that adds up to be negative 1/12. All right? So I won't leave you hanging on that. All right, a final formula. All right, so when it comes down to it, everything I've done up to this point was just trying to develop the idea, because I don't want to just throw a formula on the board and be like, there it is, now let's use it. I wanted you to understand where each of the pieces come from. But really, at the end of the day, you just need to know how to use it. All right? So here's the final formula. The integral from a to b of f of x dx, which gives you the area below the curve, right? Down to the x-axis. This will be equal to, we said capital F of A minus capital F of B, right? I'm going to add one little element to this, and you'll see why I do this after I do an example. So just write that in there, and then put capital F of B minus capital F of A. So this is the new piece in here. And all this is notation. And it helps us keep track of things. When we actually go to do a problem, that intermediate step will help us not stumble upon ourselves. You ready for an example? Okay. So let's do this. I would like us to evaluate this integral. Integral from 1 to 3 of x to the 5th dx. Now first, before I actually go and get an answer, let's try and visualize what's happening here. We have a function. What is the function? X to the 5th, which looks like x to the 3rd, kind of. It looks like this if you graph it. Okay, it's an odd function. It's a polynomial. Left side goes down, right side goes up. It goes through the origin, right? And what we're doing is we're going to 1, and we're going to 5. And 5 is way up here, isn't it? And we're trying to find the area. Make sense? Well, according to the fundamental theorem of calculus and the evaluation theorem, all I need to be able to do is find the antiderivative. And I'm in business, right? So what's the antiderivative of x to the 5th? I'm going to write that down now. 1/6 x to the 6th, right? So going back, I'm going to just write this on the board real quick. This intermediate step is what I'm doing right here. I'm writing down the antiderivative, right? I'm writing it down. What's the antiderivative? And then I'm just going to put a little bar next to this, and then put A here is 1 and B here is 3. Oh, wait, no one caught me on that. This was supposed to only go to 3. Nobody caught that. Everybody loses a point on their next test. I'm getting points. I can take points back, right? No? Okay. Only if I cuss, then you get points, huh? I see how this is. If you don't catch it, I know, but if you don't catch my errors, then I can't take points away? No. Okay, I thought I'd try. All right, does that piece of notation make sense? It just gives you an opportunity to actually write the antiderivative down. Because you've got to plug two numbers into it, right? So here's that intermediate. Now I write equals, and I'm going to have to do two computations. So I always like to put two sets of parentheses and put a subtraction between them, just to keep track of everything. And then I'm going to take capital F, which is sitting right here, and I'm going to plug 3 into it. So 1/6, 3 to the 6th, and then over here, 1/6, and then 1 to the 6th. So what is 3 to the 6th? 3 times 3 times 3 times 3, 6 times? Someone do that for me? 7, what? 729? 729 over 6, right? Because you still had a 1/6 out here? Minus, what about this one? That's just 1, right? So 1/6. And that's 728 over 6. Does that go in or no? Evenly or nicely? Yeah, you're getting a decimal. So, yeah, I'm getting a repeating decimal, right? So what I'm going to do is just leave it like this. This is our exact answer. You can reduce it. You can divide each of these by 2, but
Would it be wrong?
it would not be wrong to leave it like that, no.
Or
Or the other way, yeah. But as a decimal, I'd just avoid the decimal, yes.
reduce it to 364 over 3.
Yep, 364 over 3. And if you did a decimal, what the heck? It's not, this calculator's not giving me a decimal. What was it? 0.333 repeating. If you wrote this with a bar, then you could say equals. If you wrote the bar out here.
The calculator does it for you like 121 by 1/3.
120.
It doesn't.
Yeah, but the calculator is stopping. Like, the 3's go forever.
Yeah.
Yeah. If you're going to write this down, you want me to give you full credit, you need to put a bar on top of this. Because if not, then you're saying it's that, which is now you've rounded. You've stopped. We want the exact answer. We didn't go through all this trouble for an approximation, right? Well, we didn't go through much trouble at all, in fact, right? But someone did. No, someone proved those theorems for us, right? Okay. Questions? No? All right, this next example, this is just an interesting example. Let's look at the sine function. Sine x. Haven't you ever been sitting there on the weekend, on a Friday night, looking at the sine function and just thinking to yourself, I wonder what the area below that first arc of sine, I wonder what that must be. Like, I wonder what this area right there, just there, I wonder what that is. Yeah? Happens quite a bit, doesn't it? So, how would we set this up?
1 on top, 0 on the bottom.
Where am I going to start? 0. Where does this happen? I haven't heard it yet. Pi. Remember, the period of sine is 2 pi. So halfway is pi, right? So I would go 0 to pi. What is the function I'm interested in finding the area below? Sine x. So that's my integrand. and then dx, right? Now that is another simple integration. I hope that's simple to you now, right? Or is it one of those things where you've gotten so far advanced now that that becomes difficult for you? Your brain just shuts down? No? What's the antiderivative? Negative cosine x, right? And then my little bar here, and I put 0 and I put pi here, just to keep track. And then equals, now 2 sets of parentheses. And let's take our time here. What gets plugged in first? The pi goes first. So negative cosine pi, and then over here, negative cosine of 0. What is cosine of pi? Cosine of pi? Negative 1. Cosine of pi is negative 1. But you have negative already out there. So this is just going to be 1 minus, what's cosine of 0? 1, but then you have a minus. So minus 1 like that. So your answer is 2. Now, I don't know. That kind of strikes me as being odd. Does it strike you as being odd that the area underneath that is 2? Doesn't that seem like that's just too nice that that would be 2? Like it should be some weird number? No? 2 seems too nice for me.
Yeah.
But that's what it is.
Well, the apex of it only goes up to 1.
Yeah, it only goes up to 1 here. But why 2? It seems like for the sine curve, there's so many weird numbers on the unit circle. It just seems like why 2? But that's the way it is, okay? There's no debate about it anymore. I would just expect it to have like, I don't know, pi or something in it, or square root, or, you know, but that's the way it is. All right, so what about this? What would happen if instead of me saying what's the area of that first arc, I went ahead and just went through the whole first period of this? How would this change up here? I would have 2 pi here, and this would be 2 pi here, and this would be 2 pi here. Now let's see how that changes things. That's the only thing that would change, right? So what's cosine of 2 pi? Cosine of 2 pi is 1, right? So it's going to be minus 1, so this will be negative 1, but this is exactly the same. So your answer would be 0. Uh-oh. Does that make sense to you?
Yeah. It's almost like negative.
It's like negative. Look, this is important. This area down here appears to have counted as negative area, and it offset that positive area. And that's the way this works. If your region falls below the x-axis, it's going to count that as negative area. And if it's above the x-axis, it's going to count it as positive. Now you might be wondering, well, why in the world? Area is always positive. You can't have negative area. Well, I agree with you if you're just talking about area in general. But just go back and think about this little, remember those Riemann sums, we had little rectangles in here, didn't we? That rectangle right there, that width right here, right? That dx, that's always a positive number, isn't it?
Yes.
And then the height of it, well, because it's your y value, isn't it? It's your y coordinate, and that y coordinate is positive. So this will be a positive number also. And when you multiply positive times positive, the area of that will be positive, yes? However, when you get over here into those Riemann sums, and you have a rectangle here, then all those rectangles, you're going to have still a positive width, but now your height, right, which was the function evaluated at a point, is now going to give you a negative y value, so that's going to be a negative number. And therefore, the area of this will be negative. And so they offset each other. Make sense? Another thing I'd like for you to kind of see if you can visualize this. When you see this integral, right, from 0 to 2 pi sine x dx, here's the sine function. We're going to go from 0 to 2 pi. Just imagine, can you see a rectangle right here? And then just imagine that rectangle moving across the function, going from